Welcome to my presentation. In this presentation, we are continuing example 3 part 2 in this presentation. And then in this presentation, in the previous presentation, that is part 1, we figured out we figured out the values of eigenvalues. The eigenvalues we have determined was lambda 1 was equal to 5 and lambda 2 was equal to -1. Now we will use these eigenvalues and find the corresponding eigenvectors. To find the corresponding eigenvectors, we want to solve the homogeneous linear equation, and let me write that. Lambda I minus A times x is equal to 0. This is a homogeneous equation. When lambda is equal to 5, we'll start with lambda 1. When lambda equals to 5, we want to find the corresponding eigenvectors for this eigenvalue. So let us get that started here. So lambda I minus A times x is equal to 0. This is the homogeneous linear equation. And now we will substitute the values of eigenvalue, which is for lambda we'll substitute 5. And for the I is the identity matrix, and the identity matrix here is going to be 1 0 0 1, because the given matrix is a 2 by 2 matrix, minus the given matrix A. The elements of those are 1 4 2 and 3, like that, and all of this times x is equal to 0. Okay, now I can also write this as, if I were to distribute the eigenvalue to every one of the terms in the identity matrix, that's going to look like this: 5 0 0 5 minus the given matrix is 1 4 2 and 3, and then this times, I'm going to put a bracket like that, times x1. If I were to write this as a matrix, x1 x2 is equal to another vector 0 0, like that. Okay, now we will simplify this part of the matrix, and when we simplify that, we're going to get, we can simplify as follows. We can subtract the elements of the corresponding matrix, and when we do that, this is how we're going to come up with 5 minus 1, and then 0 minus 4, 0 minus 2, 0 minus 2, and 5 minus 3, 5 minus 3. That's what we have, times x1 x2, and then is equal to 0 0. Okay, when we simplify this some more, this is going to come out as 5 minus 1 is 4, 0 minus 4 is -4, and then 0 minus 2 is -2, 5 minus 3 is 2, and then we can write this as x1 x2 is equal to 0 0. Okay, now when we look at this first equation, we can write that out as follows. We can write that as, this is pretty much like a augmented matrix, and we can write this as 4x1 minus 4x2 is equal to 0. Now if I were to give some values for x1 and x2 and see when that condition will go to 0, it is as follows, isn't it? If I were to say, if x1 equals to 1 and if x2 is equal to 1, then that condition will be satisfied. Look at this: 4 times 1 minus 4 times 1 is going to be equal to 0. I substituted for x1 as 1 and for x2 as 1, and when I do that, that is when this goes to 0. 4 minus 4 is equal to 0. Therefore x1 equals to 1 and x2 equals to 1 will satisfy that particular equation. x1 equals to 1 and x2 equals to 1 will also satisfy the second equation, which is negative 2x1 plus 2x2 is equal to 0. When x1 is equal to 1, it will be negative 2. This will be negative 2. When x2 equals to 1, this will be positive 2. Therefore, negative 2 plus positive 2 is equal to 0. So therefore, we can come back here with this information. We can come back here and say the vector x1 and x2, the values of that are 1 and 1, like that. And therefore, these are the eigenvectors corresponding to the eigenvalue lambda is equal to 5. I'm going to write this one as not there, but all of this is what is called the eigenvector for the eigenvalue lambda equals to 5. We have figured out, or we have found the eigenvector for the corresponding eigenvalue of 5. We need to do the same thing for the next condition as well. Since we have two solutions for this quadratic equation, lambda equals to 5 and lambda equals to negative 1, we will take the second part of it and then try to solve that. So let me do that right here. So to find the eigenvector for the eigenvalue of lambda equals to, let me write this a little better. This is the second condition. When lambda is equal to negative 1, we want to find the corresponding eigenvector. Let us try that. Here again, the characteristic, the equation we have, the homogeneous equation we have is lambda I minus a times x is equal to 0, right? Here lambda is negative 1. The identity matrix is 1, 0, 0, 1. And then the given matrix is 1, 4, this is 1, 1, 4, 2, and 3. And all of this times x is equal to 0. The way we can write this one out is we're going to distribute the eigenvalue to every one of the terms inside the identity matrix, and that will become negative 1, 0, 0, negative 1, like that, minus 1, 4, 2, and 3, like that. And then we're going to take this and then we're going to multiply that by the vector, and that is going to be equal to a 0 vector, x1, x2, and then that's going to be equal to a 0 vector, 0, 0. We will simplify the matrix in here, inside this brackets here, inside this parenthesis here, and when we do that, we're going to arrive at something of this nature. Negative 1 minus 1, 0 minus 4, 0 minus 2, minus 1 minus 3. That is what we have. And then here we have x1, x2 as a vector. Let me write this a little better. This is going to be x1, x2, like that, is equal to 0, 0. I can simplify this to negative 1 minus negative 1 plus negative 1 is negative 2, 0 minus 4 is minus 4, 0 minus 2 is minus 2, minus 1 minus 3 is minus 4. So that is the matrix it simplifies to, and we have a vector x1, x2, and we have a 0 vector which is 0, 0. And now if I were to look at this equation, I have negative 2x1 minus 4x2 is equal to 0. right? And if I want to give values to x1 and x2 to see when that equation will be equal to 0. So by trial and error, if I were to say if x1 is equal to 2, if I give values of x1 as equal to 2, and if I give the value of x2 as equal to -1, that would satisfy the condition, isn't it? Look at this. -2 times for x1 if I substitute 2, minus 4 times if I substitute -1 for x2, that should equal to 0. So -2 times -2 is -2 times 2 is -4. -1 times -4 is +4, and therefore -4 plus +4 is equal to 0. Not only that, it also should satisfy the second equation. The second equation, what we have here, is -2 x1 minus 4x2 is equal to 0. And if we were to substitute the values of x1 as 2 and x2 as -1, that should satisfy that. This is going to go to -4, and this is going to be +4. Therefore, -4 plus +4 equal to 0. And therefore, x1 equals to 2 and x2 equals to -1 satisfies both these equations. And therefore, we can come back here and then say x1, x2 is a vector, and the values of this vector are 2 and -1. So these are the eigenvectors corresponding to the eigenvalue lambda 2 equals to -1. So let me write that here. This one here is called the eigenvector for the corresponding eigenvalue lambda equals to -1. So to sum up what we did so far, we have solved a homogeneous equation. We solved a characteristic equation of the determinant of the given matrix, and we arrived at a polynomial in lambda. And when we simplified that equation using the quadratic formula, we came up with two solutions: lambda 1 equals to 5 and lambda 2 equals to -1. Those lambdas, lambda 1 and lambda 2, those are the eigenvalues. For those eigenvalues, we wanted to find the corresponding eigenvectors, and therefore we took those eigenvalues, and then knowing the homogeneous linear equation lambda I minus a times x equals to 0, we were able to arrive at the eigenvectors for those corresponding eigenvalues. So this is the way we can use this procedure to solve problems to determine the eigenvalues and the corresponding eigenvectors. In my next presentation, we shall look at some more examples related to eigenvalues and eigenvectors.